class, welcome to lesson 52. In this lesson, we're going to talk about Bronsted-Lowry acids and bases on the reagents. They call these Bronsted-Lowry acids and bases alternate acids. And we're going to compare these alternate acids to Arrhenius acids and bases. Let's get started. So, the reason why we have these Bronsted-Lowry or alternate acids and bases is because the Arrhenius definition of acids and bases is too limiting. Recall that Arrhenius acids are substances that have the hydrogen ion as the only positive ion in solution. And Arrhenius bases are substances that have the negative OH hydroxide ion as the only negative ion in a solution. But the problem with this definition is Arrhenius acids and bases must be in water to make an aqueous solution. So alternate acids and bases are acids and bases that don't necessarily have to happen in a solution. An alternate acid is a substance that donates its hydrogen. So it has more hydrogen than it needs and it donates it. You can remember this because the word acid has a D in it. So the acid is the donor for the hydrogen. And bases are the acceptor for the hydrogen. Again, acid with a D donates. Except base and acid both have an A, so there's no good way to remember that. But again, acid, D, donate. Notice from this picture here that the alternate acids and bases are just a more broad definition. So all acids and bases are going to be alternate acids or bases, but only some acids and bases could be Arrhenius. And when we talk about the alternate acids and bases, it's really important to remember that the hydrogen ion is also going to be referred to as a proton. Particularly in biology, we talk a lot about these proton acceptors and these proton donors. Now we're going to have Sydney show us how to identify alternate acids and bases. Okay, guys, so now we're going to have my daughter teach us about acids and bases according to the alternate theory.
So, the alternate acid and base pairs is that the acids will donate one H to the base, which will accept the H. And we can remember this because there is a D in acids, which will stand for donate.
How about acid-base conjugate pairs?
Well, acid-base conjugate pairs are two chemicals, and they're identical, except their formulas are different because the acids will have one more H than the bases.
Okay, let's see if we can apply that rule to these questions.
Well, for this one, this is NH3, and over here is NH4, which is it.
Why are those paired up? You're right.
They're paired up because this one has 3 H's and this one has 4 H's, and we know that this one is the acid.
Just write an
A. And this one is the base because this one is greater than the base.
Okay.
Well, over here is H2O. And this one is its pair. It's paired up because this has 2 H's, while this one has 1 H. So, furthermore, because we know that this one is the greater one, this one would have been the acid, and this one would have been the base. And to the left of the arrow, which is here, are conjugates. So this would have been the
Put the C in the front.
the acid conjugate.
In the front.
Oh. Acid conjugate.
Conjugate acid.
Conjugate acid. And this one would have been the conjugate base.
That's awesome. So a couple things to realize is we have just the base and the acid on the reactant side, and on the product side we have the conjugate acid and the conjugate base. Now notice how this reaction is balanced. It is balanced because we have the same number and kind of elements on each side. It is also balanced in charge, as this has 0 charge and this has 0 charge, so there's 0 charge on the reactant side. And here we have a positive and here we have a negative, so they cancel each other. So we also have 0 charge on this side. One more thing. Sometimes you might have a double-headed arrow. It does not change how we approach the problem.
So over here is HSO, and this has 1 H. Over here, this is SO, and this has no H's. So they're pair because over here, this formula has 1 more H than this formula, and we can use that information to know that this is the acid and this is the base. Over here, we have H2O. Over here, we have H3O. They are pairs because H2O has 2 H's and H3O has 3 H's. And this formula is greater than this formula. And again, we are going to use this knowledge to know that this is the acid and this is the base. Again, searching for the conjugates to the right side of the arrow again. This would have been the conjugate acid and this would have been the conjugate base.
All right, very nice. Last one.
Over here is H2CO. Over here is HCO. This one has 2 H's, and we know that from the subscript, and this one has 1 H. So this one would have been more and this one would have been less, making this the base and this the acid, and both of them pairs with each other. Over here, we have OH, and over here we have H2O. These are pairs because this only is 1 H right here, and over here, this is a 2 for 2 H's. So using that, we know that this is the acid and this is the base. And again, to the right of the arrow, we are looking, this would have been the conjugate base and this the conjugate acid.
Very good. So one important thing to note from Sydney's awesome work here is that in the alternate acid-base theory, sometimes water is an acid and sometimes water is a base. It really just depends on the reaction and what it's paired with. So by now, you should be able to define an alternate acid and base. So remember, the big difference is an alternate acid and base are all related to just the hydrogen. And the biggest difference is the Arrhenius base has to have hydroxide, but the alternate base just has to be a hydrogen acceptor. So by now you should be able to define alternate acids and bases and compare Arrhenius and alternate acids and bases. That's it. You've done it. This is the end of lesson number 52 on alternate acids and bases. Make sure that you've taken good notes. Write down any questions you have and bring them to class. Complete your homework on Google Classroom and Make sure you have your materials so you're ready for next class. I'll see you soon.